All right, so today we're going to finish up the unit by just looking at word problems. So there's nothing really new in this section. It's just kind of taking everything we've done so far and applying it to problems. So exponential functions, right, are going to be functions where their variable is in the exponent of the equation. And by looking at the base of the exponent, we can tell whether something's like increasing or decreasing. So we want to make sure that we've got all our algebra steps down so we actually understand how to solve these problems. All right, so let's look at the first example. And what we have is the following equation. All right, and C is going to be temperature in Celsius. Oops, forgot. It's an S. Can't spell today. And T is going to be time in minutes. Okay? So when we do the money problems, right, the time always has to be in years because we're talking about an annual interest rate, right? But when we're talking about just general exponentials, we can use any unit of time that we want. So this is going to be the temperature of a sandwich, right, after T minutes. And we want to answer a couple of questions about this. So the first is find the initial temperature. So there's two ways you could do this. You could just look at it and figure out what it is if you understand the structure, right, of an exponential function. So that coefficient out front is typically the initial value. That's how the money problem worked. That was principal. So if you just looked at it and said it's 25, that would be fine, right? The other way you could think about doing this is you could say, well, I'll just plug in time 0, right? So if you plug in t equals 0, well, the 0.91 to 0 is going to turn into 1, and you're going to get 25 times 1, you're going to get 25 either way. So the initial temperature is just 25, right, degrees Celsius. So part B wants to know, does this function represent growth or decay? Somebody got a guess?
Decay.
Decay, why?
Because it's going to get lower temperature.
The base is less than 1. So it's a reducing function because the base of the exponential is less than 1, right? And it would be a growth function if the base was more than 1. So this is going to be a decay function, right, or decreasing, right? And part C wants to know, well, by what percent does the temp change each minute? Okay? So what this is really asking you for here is, this is another way of saying find the rate. So every one of the standard exponential functions we've looked at, even the money problems, right, we said can be reduced down to a times b to the x, where b, right, is 1 plus r. So that r value is positive if you are a growth function, and that r value is negative if you have a decay function. So if we look at the function we started with, well, a was 25, the initial value. B was 0.91. So some of you may be able to just look at that 0.91 and figure out what the rate is, just kind of working backwards. But if you can't, that's okay. So B was 0.91. That is equal to 1 plus the rate. So now when I subtract 1 from both sides, I get R is negative 0.09. And so I expected a negative r because this is a decay function. So the rate was negative. And I did that math right? Yeah, 0.91 minus 0.09. So this works out to be, right, negative, 9%. So the rate will always be, right, the percentage in decimal form, and you have to multiply by 100 to get it back in percent. So the question wanted to know by what percent. So it's dropping 9% every minute.
Do we have to put the negative even though we already said it was?
Yes, because it's saying by what percent does the temp change. And so you need to say if it's a positive rate, you're saying it's growing. If it's a negative rate, we want to apply that it's a negative rate. And when you solve for it, you get a negative. Now, if you wrote it out in words, it's dropping 9%. Well, the word dropping implies negative. But the reason I would say you should just kind of get in the habit of thinking like that is because sometimes we can give you problems where in the question we need you to set up the problem. And we might say decay, decreasing, something like that, and you have to know to throw that in as a negative value into the equation. So you should just kind of get in the habit of all growth rates are positive, all decay rates are negative when you're dealing with it. All right, so that one was pretty straightforward. So now, we want to look at this equation. So we have 9 plus 11.028t. So the last problem was exponential decay, right? This is going to be continuous. Now, is this going to be growth or decay?
Decay? Is the exponent less than 1?
Is it the exponent that determines?
Because it's positive.
Oh, because...
So on this guy, right, when you're talking about continuous, the base is always e, right? But it's the rate. If the rate is positive, it's a growth. If the rate is negative, it's a decay. So because that exponent is positive 0.028, it's a growth function. And we can actually see that the rate is 2.8%. Okay, so it's growing. If we'd had a negative in front of that, then it would have been decaying, right? So in this case, what we have is C is once again going to be measured in Celsius. T is going to be measured in minutes. And we're putting a water bottle inside the cooler. As it cools, oh, so my bad. It turned out as a question mark on mine, but that is actually supposed to be a negative sign. I couldn't understand why there was a question mark in the equation, but now I get it. It read it as a, didn't know what to read it as. So this water is cooling, so this is in fact going to be a decay, and it's decreasing by 2.8%. So we're putting a water bottle in a cooler, right? And we want to know how long until the water is cooled to 14 degrees Celsius. And T is going to be the number of minutes since we put it in the cooler. So if we want to know when the water is 14, right, well, what we need to do is set this equation equal to 14 and then solve for T. So we'll say that 14, right, equals 9 plus 11e to the negative 0.028t. We're going to subtract 9 from both sides and get 5 equals 11 to the 0.028t. And then I'm solving for t, but before I can take the natural log, I need to get rid of the 11, so I'm going to divide both sides by 11. Since our base is e, the most logical thing to do is to take the natural log of both sides. So I'm going to take the natural log of the left, and when I take the natural log of the right, it's going to cancel the e, and I'm just going to be left with the exponent. So one thing you should keep in mind is time in this equation should always come out to be a positive value, but it's very difficult for people to sometimes tell whether a natural log is going to be a positive or a negative. So if you think about the graph of natural log, right? It looks like this, and its intercept is 1, 0. So any values inside the log that are bigger than 1, you're going to get a positive natural log. But any values that are inside the log that are less than 1, you're going to get a negative value. So the reason I'm bringing this up is the next step of my algebra is to take this thing that looks like it would be positive, because you don't see a negative sign, right? And then I'm going to divide it by a negative number, but you are in fact going to get a positive time, because 5 over 11 is less than 1. So the numerator of this is actually negative, okay? So we're going to get the natural log of 5 over 11 divided by 0.028t. And so I've seen students on exams try to be clever, and they would see this and they would be kind of like, oh crap, I'm going to get a negative time, and they would just drop the negative sign out of the denominator when they don't realize that this is also a negative number. So this will work out to be positive. So if I'm going to do this on here. So if we say the natural log, right, of 5 divided by 11 divided by negative 0.028, and you see we do in fact get a positive value, and it's 28.2 minutes. So it's going to take a while for this thing to cool. All right. Any questions on that? Okay. So this next problem, we actually had a version of it on a previous final. It kind of hit people out of nowhere, but it wasn't meant to be that hard. We got some really funny answers for one of the parts of the problem. So this is a function where h is going to represent the height of a tree. So h is measuring height. T is obviously time, and we're measuring it in years. So T in this case would sort of be like the age of the tree, right? And we can plug it into here and figure out how tall is this tree. So if you just look at the rate, right, it looks like that this thing is decaying, right? But we've actually moved the exponent into the denominator. So we're going to actually analyze what's really happening here. But trees grow, so this should be increasing, right? So what we're going to see in a little bit, though, is that negative 0.2 is it's growing, but at a decreasing rate. So when we kind of move that e into the denominator, it's getting bigger, but as it gets bigger, instead of growing exponentially, kind of like a traditional exponent, it's going to actually get smaller over time. Kind of like when we looked at the compound interest formula, and we saw that as we let n get bigger and bigger and bigger, we were still gaining money, but we were just gaining less money as we made n bigger over time. So if we look at this guy, right, we're going to answer a couple of things. The first thing says, right, well, what is the height after 11 years? So this is pretty straightforward. It just wants to know what h of 11 is. So we're simply going to plug 11 into the function. Now, if we want exact answers, that would be it, okay? If we let you approximate, which we're going to do this, and we're going to round to 2 decimals. So you have to type the entire function into the calculator, or you're not going to round right. So I'm going to see if I'll get this to show up on here, right? And show you how to do this. So we're going to say, well, the numerator is easy. It's just 120. Then when we do the denominator, I need to open a parenthesis so I get this whole expression in the denominator. We're going to say 1 plus 200, and then I'm going to raise it to e. Okay, and in this one, this calculator, e actually goes into the exponent. It superscripts it. But if your calculator doesn't, you have to open parentheses for the exponent to make sure you get all of this stuff in the exponent. So we're going to get negative 0.2 times 11. And then if your calculator does do what this one's doing, right, you actually have to hit that arrow key over to bring the cursor back down. And now you can close the denominator. So when we hit enter, we see that the tree is 5.18 feet, I guess is what we're measuring it in. Yeah. So one of the things that I would do with these problems is go home and practice, and it seems so silly, but it's so important. Go home and just re-enter these equations on your calculator that you're going to use on the test and make sure you're getting the same answers. Because it's very, very frustrating to me when someone's doing the work 90% of the way there and they're just missing points because they didn't know how to use their calculator or they didn't know an algebra step. So it just seems like a silly thing to do, but you want to practice using the equipment. All right? So part B says, well, when right? So when is the tree going to be 70 feet tall? So how long? So solving for t is going to be the most difficult thing algebraically for people to do. So in this one, because the equation's set up a little bit differently, right? We're still going to set it equal to 70, but you'll just see we have just a little bit more algebra involved. So we're going to say, well, 70, right, is going to equal 120 divided by 1 plus 200 e to the negative 0.2t. So the whole goal here is to solve this for t. So the only way to get t out of the denominator is to multiply both sides by the entire expression in the denominator. So you need parentheses. I then want to divide both sides by 70. There's no reason to distribute the 70, right? We only do that when we need, we have kind of a variable here, but I can just go ahead and divide this constant by this constant. So 1 plus 200 e to the negative 0.2t, and 120 divided by 70 is just 12 over 7, because the zeros cancel at the end of the tens. I don't want to get a fraction here because I need to get this exact time. All right, so then I'm going to subtract 1 from both sides. And just to make my life a little easier, well, 1 in terms of 7 is 7 over 7. So the right side of this equation is now 5/7. Everybody see that? Did you just get a common denominator? Okay. So now I need to divide both sides by 200. Well, before I do that, let's rewrite on the right. Let's rewrite this with a positive exponent. So e to the negative 0.2t, right? When I rewrite it, I'm going to get e to the positive 0.02t. This equals 5/7. And so now I have a fraction equaling a fraction, so I can cross multiply. So 7 times 200 is 1400, right? That's going to equal 5e to the 0.02t. 1400 is divisible by 5, and I get 280.
It's just 0.2, right?
It is 0.2. Why did I change that to 2%? Because I'm so silly. Thank you. Yep. Yep, it is 0.2. All right, so now that I'm here, I can take the natural log of both sides. And so the natural log of 280 divided by 0.2 equals t. And let's see what that gives us, just to get an approximation. And we get about 28.17 years. So solving for time, right, is the kind of most challenging part, but if you just methodically take it step by step and just unpack it, It's actually not as terrible as it seems. You just have to keep undoing everything till you get down to the very last step. So there was a part C to this problem when it was on the final. And part C said, well, how tall is the tree after a very long time? And sort of what it was kind of asking is, what's basically the tallest these trees are ever going to get, right? Because there is a limit of how big a tree can grow, right? So one of the things we were kind of checking for is, well, do you understand or can you read the equation and figure out what's going to happen over a very long period of time? And that's really sort of a lead-in to something you would do in calculus. So this was the one where we got some very, very creative answers. And we were pretty lenient on how we graded it because we were just trying to ask, figure out if you could come up with something. So here's what I would do. Whenever I get stuck, I like to rewrite the equation, right, with positive exponents because I want to see what's truly in a numerator versus what's truly in a denominator. So one of the tactics some students used was they started just plugging in really big values of t. And they started to notice that as they let t get bigger and bigger and bigger and bigger, it sort of was capping out at a number, right? You don't really have to do it that way. So if we look at this, and this is sort of what you would be asked to kind of do in calculus, right? Well, now when we write the equation like this, the numerator is locked at 120, right? But the question is, what's happening in this denominator? So let's just ignore the numerator for a second. So the denominator, you have 1, right, plus 200 over this stuff. So the question is, what is happening to e to the 0.2t as t gets really, really big? So the question is, what happens to exponents, exponential functions, right, when you let the exponent just get huge? And now that I've rewritten it like this, e is to the positive 0.2t. So if you think of the graph, right, e is a base bigger than 1, right? So what does the graph of b to the x look like when b is greater than 1? Yeah, right? It just vertically shoots up to the sky, right? So as t is getting very, very big, this number is just growing astronomically big, okay? So then the next question is, all right, well, let's just look at the 200. We're just looking at this piece of the equation, okay? So what's going to happen to the number 200 if you just keep dividing it by a bigger and bigger and bigger thing? So let's divide 200 by 10. What do you get?
20.
Okay. Divide 200 by 100. Divide by 1,000. Just keep moving to the decimal place, guys. That's why I'm picking these numbers, right? So we went from 200 down to 20, down to 2. So then it's going to go 0.2, 0.02, 0.002, right? If you just keep adding a 0 to that denominator, right, it's just going to get smaller and smaller and smaller and smaller. So this exponential function in the denominator, as t gets really, really big, right, as the denominator of a fraction gets huge, the whole entire fraction is going to 0, okay? So what's going to happen here is the following. When we rewrite it like this, right, as t goes to infinity, right, as it gets really, really big, 200 over e to the 0.2t is actually going to 0. So, and you can just imagine, right, if I picked a value of t that made this 10, right, and then made it 100, and then made it 1,000, and then made it 10,000, right, you would just see that whole fraction collapse to 0. So if you go back to your original equation then, well, if this piece of the puzzle is dropping to 0, then what are you left with? 120 in the numerator,
So it's just
and 1 in the denominator. So the tree's kind of going to cap out at 120.
If you graphed that, would it have an asymptote? Like, would it ever?
Yes, that's exactly what would happen. So if we graph this, all right, so when e is 0, or when t is 0, excuse me, when t is 0, right, this whole denominator becomes 1, and you just get a 200 here. So you would get 120 over 201, right? That's, let's say about 0.5, just to estimate roughly. So the tree's not going to start as a sapling at, we're not going to start it at a seed, right? So the graph is going to look something like this. where you have a horizontal asymptote at 120, right? So it's getting bigger, right? But it's getting bigger by a little bit less over the years, and it's going to just start approaching 120 feet, and that's probably going to be the max height of this type of tree. And so that was kind of the idea here. When you wrote it like this, you would just, and if you actually just kept plugging in big values of t, what was happening is this piece of the equation was turning to 0. And then most people were getting, oh, it looks like it's approaching 120, okay? So the idea is, as the denominator of a fraction just gets bigger and bigger and bigger, the whole fraction collapses to 0. But what we actually had going on here was a complex fraction, right? We had a fraction within this bigger fraction. And so it was just that piece was dropping to 0. So as t gets really big, this part of the problem is going to go to 0, which means the height's just going to approach 120, and that's exactly what the graph would look like. It would look like a horizontal asymptote. So in Calc 1, you're actually going to do something involving limits to infinity, and what you're doing when you take a limit to infinity is you're analyzing, well, what happens to this equation as the variable gets ridiculously big. And one of the things you're going to see that we use limits to infinity for is to find horizontal asymptotes of graphs. So if the limit to infinity existed, like this one did, the limit would be 120, that would tell us there is a horizontal asymptote as the graph approaches infinity, and so it gives you an idea of how to curve sketch. So one of the cool things you're going to do in calculus is you're going to use some of these techniques, and you're going to be able to draw a graph with pretty good accuracy, and you can look for specific attributes a graph might have by doing different calculations on them, or computations, I should say.
What was the wording of this one?
The last question just said, how tall is the tree after a very long time? Yep. Mm-hmm. And so what we mean by a very long time is that's a way of saying as t approaches infinity. If we just throw that at you, people freak out because like, how do you plug infinity in, right? We don't really deal with that. But we actually already played with this idea in here when I showed you that if you take the compound interest formula and you let n go to infinity, you just keep blowing up n, that whole middle part of the formula just turned into e. So the compound interest formula and the continuing interest formula are exactly the same. It's just in continuous compound interest, we just let n blow up to infinity, so we just call it e. And we don't have to type in a value for n, but it is in fact the same value. So if you ever get into trouble, right, a valid technique, and when you first start learning limits to infinity, the way we do it is we have you set up a table and we actually have you physically plug numbers in. But we know, just like when we learn graphing in here, that's a very cumbersome and inefficient way to do something, but it will get you part of the story. And so some students plugged in values, some students were able to understand that that was going to 0, and some students just gave us some hilarious explanations of what they thought was happening in the equation. Some people just got really existential. I think one person said something about gravity. Oh, that the tree was going to grow and then it was going to die and turn back into a sapling and then start all over again. And that was probably my favorite. We got this along like, and you could just tell the person was just like, just wrote a story. So the idea is, you know, math is a language, and if you really break the problem down into parts, you really only have to really worry about where's the variable in this problem, right? Now, the other way you could have thought about this equation, just really quickly, just show you another way of thinking about it, now that you kind of understand what happens over a long period of time, well, if you just look at this part of the equation, just the 200e to the negative 0.2t, well, just that one little piece by itself, that's a decay function. And the graph of a decay function, right, it decreases over time. So you could have looked at this directly and said, oh, well, that's going to 0. So I'm going to get 120 over 1. Because we know that that piece is just going to collapse down to 0. So some people could see it in the original problem. Some people can think of it better if a denominator's going to 0. But either way, you would have gotten that it reduced to 120 over 1. All right. So we have two populations, all right, of bacteria. And the first one has a growth rate of 0.15. So notice that the percent symbol was not given after this. It didn't say 15%. If they just give you a growth rate, then you don't have to make any adjustments to it. You get to plug it in directly. It's already in decimal form. So this growth rate is 15%. We just it was given in this problem as 0.15. All right. And we've got an initial population of 3,000. The population in the second dish has a growth rate of 0.08 and an initial population of 5,000. These are two different bacteria growing in two separate dishes. And the first thing we want to do is find when the population are of equal size, and they want an exact answer, which means no putting in the calculator, no decimals. All right. So in this problem, it said growth rate for both dishes, so I knew to make R a positive number. But if it had said, like, we were exterminating something and they were dying off, and they said decay rate or decreasing, then I would have had to mathematically make it a negative number. So you want to make sure that you're careful, because sometimes we can just use words that imply decreasing, but you have to put in that negative sign on your own. All right, so what we need to do is we need to set up an equation for each population. So you're allowed to assume, there's actually two ways we could do this. We could think of it as exponential growth, right? Or we could set it up as A times B, right, to the R. So if I did the A times B method, well, since this is growth, my B for the first one would be 1.15, right? And for the second one, I would get 1.08, okay? I can also use E. I personally think E is a little bit better because I get to use natural log to wipe it out whenever I need to. So I kind of tend to just default to PERT is kind of what we call the formula, right? So this is, right, the initial population, right, E to the RT. So E to the R, right, is going to turn into 1.15 or 1.108 anyway. All right, so for the first population, P1, we have 3,000 E to the positive 0.15 T. And for the second population, P2, we have 5,000 E to the 0.08 T. So I have a little bit more algebra tools if I use E. So now I want to know when these two things are equal, so I'm just going to set them equal to each other and solve. So a nice trick, if you take advantage of what we know about exponents, is I want to move all the e's on one side and I want to move all the whole numbers to the other. So what I like to do is find the bigger rate, because I want to do positive things. So the bigger rate is 15%. So it would make more sense to me to divide both sides by the 0.08 rather than the other way around. So on the left here, I'm going to get E to the 0.15 T divided by E to the 0.08 T. So that means that I had to divide both sides by 3,000, right? So I brought the 0.08 over and I brought the 3,000 over. Yep.
How do we know not to do 1.05?
It does, you can totally do that. I was saying there's two ways to do it.
But when you do E, you just leave it.
Is
it continuous?
Yeah. If they don't say n times a year, right? And the A, B to the T, that is continuous growth, right? So you could totally have set it up that way as well. That would have been fine, and you're going to end up getting the same answers. I just personally, like, knowing continuous growth is E, I like it a little better because then I can use like natural log when I'm doing the algebra and I can just wipe things out. The numbers are cleaner. But you would have had two different bases, right? And we saw in the exponential problems how hard it was to solve for something when you had two different bases, right? You're still going to end up with natural logs all over the place. But this works out to just be a little bit nicer. Okay, so now what I can use is my property of exponents over here. So what's the rule if you have the same base and you're dividing? You subtract. So that's why I like to put the bigger rate on top. So I just end up with a positive exponent. So really it's just what's 15 minus 8, and it's 7. So the left side reduces to e to the 0.07t. And on the right, 5,000 over 3,000 is just 5/3. So now when I take the natural log of both sides, I just get 0.07t on the left equals the natural log of 5/3. So t is the natural log of 5/3 divided by 0.07. So up front, it looks a little bit uglier, right, with the e's, but algebraically, you just, being able to take that natural log like that, it just makes it a lot cleaner when you go to do the algebra. Now, they want an exact answer, and this is it, but I am going to put this in your calculator just to give us a reference. And was this in... It doesn't give us a unit of time here. So I don't know if this is in hours. I don't know if this is in years. It's probably hours. So at about 7.3 hours is when these populations are equal in these dishes. It could be days, right? We don't know how fast this bacteria grows. All right, so if you did this the other way, right? If I set up my populations like this, where P1 was 3,000, 1.15t, and P2 was 5,000, 1.08t. If I set those two expressions equal to each other and solve for t and type it in the calculator, I should get that exact same number. So if you just want to practice with some algebra or doing some problems, not a bad exercise to do. But you'll see you will in fact get the same answer. And what's going to be funny is when you do the algebra that way, you're going to end up with natural log of something over natural log of something, and then there may be another number out front. And if you actually look at what you did, you use the change of base formula in the, and that's why you get the same equation, right? Because I said the change of base formula, you can change something from any base to any other base that you want. And so you don't really realize that's what you're doing in that problem because it's organically happening through the algebra steps. But that's when you compare the two final answers, you'll see that it's really just taking my answer and changing the base to a different answer. Even though it'll still look like natural log, that's sort of what's happening. All right, so there's a part B to this. And the question is, well, how large are the populations at this time? So we ask you questions like this a lot when we like use bank accounts. We might give you two different banking account scenarios. So we'll say, when are the accounts equal? And then we'll say, well, what's the value of the account at that time? So in this case, we want to know how many population. So you can give an exact answer, or you can round to the nearest whole number. Okay? So if you want to round to the nearest whole number, you better not plug 7.3 into the equation, because that's an intermediary calculation. You have to use the exact time value, and then you can round at the end of the problem. So it doesn't matter which one of the original two equations we plug that t into, we should get the same population, because that time is when they were equal. So I'm just going to pick P1 just because 1 is before 2. That's it. It's just completely arbitrary. All right. So P1, right, said 3,000 e to the 0.15 t. So now I need to plug my t in. And so here's how I'm going to do that. So I'm going to multiply 0.15 times this answer. So what I'm going to get is 0.15 divided by 0.07 times the natural log of 5/3. So there is no clever reduction I can do here. The only thing I can do is divide 0.15 by 1/7, but that doesn't reduce nicely. The e is not going to cancel the natural log unless I move this in as an exponent, and that's actually going to make it worse, probably not better. So your best bet is just to go ahead and type it in like we see. So this is actually our exact answer, but I want to show you kind of how to type this in appropriately. Make sure I get us under the light so you can see the screen. All right, so we're going to have 3,000, right? Then we're going to take our E, and what we need to do here is I need to put parentheses around this fraction. So 0.15 divided by 0.07, and then I'm going to multiply, and this calculator knows the order of operations, natural log of 5/3. So then I'm going to close the parentheses for the natural log, close the parentheses for the exponent, and I get 8,964.1. So it told me to round to the nearest whole number. So we'll just say 8,964. This means if I plug this same t into the other equation, I should get this exact same number. All right, so there's one more thing that I want to show you, and it's a great life hack for when you're doing these problems. I will totally allow this move on your test as long as you do it correctly. So this is all you're given for this question. You're given that it takes 3 hours to triple, and we want to know how long does it take for it to double, right? Another way we could ask this is, how long does it take for a population to quadruple? Or I could say, at what rate does it happen? And I don't have to give you any other numbers, all right? So here's what's going to happen. This is why it's also good to assume, right, if it's continuous growth, they don't say it compounds in times a year, you can always start with E. So let's look at what's going to happen. So if a bacteria triples in 3 hours, what that means is if I start with my general formula, right, then at 3 hours, I have 3 times my initial value, right? So you just set the amount equal to 3 times the initial. And I see here, right, that our time was given, so I get R times 3. So the very first step that's going to happen is those P naughts are going to cancel out. So this trick that's really cool, right, says, well, if you're asked to find a multiplier of your original population, so doubling, tripling, halving a percent, like when are you down to 5%, right? That's a multiplier, right? You would say 0.05 times your initial population. Whenever you're asked to do a multiplier, right, the very first thing that's going to happen is that P naught's going to cancel. That's why they don't have to give it to you, okay? So then what we're left with is the following. 3 equals E, in this case, to the 3R. So then the very next step I would do is I would take the natural log of both sides. So now there's the rate at which this bacteria is growing. So if this is the rate, well, it says, well, then how long will it take it to double? So if you actually compute out the time, you better get a number less than 3, right? Because it has to double before it can triple. So now what I would say is, well, if I want to know how long it takes it to double, right, well, then 2 P naught equals P naught e to the RT. All right, P naught cancels. And here's a nice trick. Notice I didn't plug in that R, okay? You don't have to plug in all your numbers right away. right? It's very cumbersome to put all that stuff up in the exponent. So I can plug in r whenever I want. So I might wait till it's a little more algebraically convenient, right? So now I'll take the natural log of both sides. And now that I've gotten rid of e and r's in this point, well now, okay, well now let's plug in r, right? Because I'm plugging in this fraction. Because the rate is the same. So now to solve this for t, multiply both sides by 3, right? And divide both sides by natural log of 3. So that would be my exact answer. If I actually type this in to my calculator, I'm predicting I'm going to get a number less than 3. And I do. I get about 1.89 hours. So the shortcut that I want to show you, other than showing you don't have to plug everything in up front when you're dealing with the exact answers, is the following. Look at the pattern that emerged here in each of these problems when I did this, right? I started with a multiplier times my initial population. And if you look over here, right, when I got to the fourth line of algebra on the left, I had natural log of the multiplier, right, equaled RT. I just happen to have a time there. If you look over here on the right, I got to that spot after 2 lines, right? Because I just kind of jumped, I didn't have to show as many steps. But I got the multiplier equals, or natural log of the multiplier equals RT. So here's kind of a cool algebra hack. Right? If you want the rate or time to reach m times p naught, where m is just some multiplier of your original population, then m times p naught, right, will equal p naught e to the RT, and the natural log of m you will always algebraically get to that line. So you can actually just start there. So it's really, really helpful. So then once you're here, if they want you to find the rate, well then you'll divide by t. If they want you to find the time, then you would divide both sides by r. But whatever multiplier you're using, the next step is take the natural log, and you'll always end up here every single time. And so that's a really great kind of little hack to have when you're doing these.